So you may know about the idea of the concatenation of two strings. For example, if we have the string 1 concatenated with the string 1, then this gives us the string 11. But is there a way that we can make this idea of concatenation more numerical to the point where it can be used in equations, and we can also define certain numbers based on operations of their digits in these equations? Well, let's think about it. So first, for concatenation here, you might be able to think of it as a sort of linear operation. Basically, what we want to do is with the first number is multiply it by some constant to basically make space for the second number, and then we can add the result to that number, right? So if we think about this case with the 1 concat 1 is equal to 11, basically if we multiply the first one by 10, so we get 10 times 1, then we get 10, and then plus 1 is going to give us 11. Or if we have the example of, say, something with, if we want to concat with something with two digits, then we're going to have, for example, 1 concat with 23, which should be 123, right? And we can think of this as scaling the 1 by 10 squared, or 100, and then we can add the 23 to get 123, right? And so this pattern basically persists, where the concatenation is basically 10 to the number of digits of the second number times the first number, and then plus that second number. So we can write this as a concat b is equal to 10 to the, and I'm going to use this notation for the number of digits of this number, but basically a hash sign and then b times a and then plus b. And now we're assuming that all of these operations right now, we're just going to deal with the positive integers including 0. We don't really know anything about decimals yet, but we can keep it strictly in the positive integers and 0. So now here you may also notice that if we have 0 as the first number, 0 concat with anything will always just give you that other thing, right? It doesn't really have any effect if it's at the if it's the first number. If it's the second one, though, it still works in a way that makes sense, right? Where you basically multiply by 10, right? When we have this here, and we can think of 0 as a one-digit number too, and that will make this work. Now, for the idea of using them in equations, it might be useful to also have an inverse operation, which I would like to call deconcatenation. Now, this doesn't necessarily make as much sense as normal concatenation, but it can be used, it's going to help more in equations, basically. So if we have something like, now if we want to remove this, so if we have 123 deconcat 23, this should be equal to 1. This is what we basically want. And basically it's like an O with a minus, and then we show arrow like a direct subtraction, basically. Same with concatenation, we have the plus though. And so with this, well, we basically want it to be a sort of inverse operation of concatenation. And so we can use the idea that A concat with B, deconcat B should be equal to A, and then basically from this we can try to invert it to solve for A. So if we take this and then we plug in the definition for A concat B, so we're going to get 10 to the number of digits of B times A plus B, right? All of this, and then we deconcat B. And now if we just take this basically as our input, which I'm just going to denote as these two lines here. But basically, if you want to get a from here, what do you have to do? Well, you first need to subtract b. Then all we have is 10 to the number of digits of b times a. So then all you need to do is then divide by 10 to the number of digits of b. So now with this, we have that a deconcat b is going to be a minus b over 10 to the digits of b. Now, there is a problem, which is the fact that what if you don't have something here at the end that you can, basically clip off, right? Deconcat off. Well, it would be nice to say that doesn't really make sense. So we can say that it's undefined. Well then, how can we state the conditions that it is defined, right? Where we have this part here that we can clip off. So basically, we can say that this is defined if there exists some c element of some positive integer c, where we have that 1 is less than or equal to c is less than or equal to the digit count of a, such that, and now I'm going to use this sort of notation for it's like an index summation, right? But in this case we have concatenation, and we'll talk more about it later. But basically, if we have this concat sum from k is equal from c to the digit count of a, it has to be equal, and now I'm going to use this notation for basically the kth digit of a, and this has to be equal to b. So this is what we mean by some part of it at the end needs to exist that equals the second number, so that you can clip it off basically. And then otherwise we'll just say it's undefined. Now we have this digit count here appearing a lot, so it would be nice to also be able to define this properly as its own thing. So let's think about it from a case of scientific notation, right? So if we have some number x, which I'm just going to assume here is part of the natural numbers, right? But if we have some x, and we're gonna write its digits here as subscripts, but basically in scientific notation, base 10, we're going to have basically the first digit, x1, with a decimal, and then the second digit, and then the third digit, and then so on until we have our nth digit. And so because of this part here, we're always trying to preserve the first decimal place, or like the first part here, to be a whole number part. When you multiply by 10 to some power, we're not just going to have 10 to that digit count. We're going to have, because this is here, we're going to have 10 to the digit count of x minus 1. Okay. And now, a way that we can simplify this is, hey, let's just take the logarithm of both sides. In this case, because we have multiplied by 10 here, we can take log base 10, right? So again, I'm just going to do log without any index to be, any subscript to be log base 10 for the rest of this video. But just remember that, yeah, for this case, it's log base 10. So we're going to have log base 10 of x is equal to log base 10 of, now we have this part, x1 dot x2, x3, all the way to xn. And now, again, because of the product rule for logarithms, it becomes a sum. And then we also have 10 to some power, right? And then so that basically comes out. So what we get is then just plus digit count of x minus 1. And now, by scientific notation rules over here, this basically, if we call this c, this has to be at least 1, and then never past or never reaching 10 basically. And then what that means is that if we take the logarithm, log base 10, we're going to have that this is always going to be less than 1. Now what we want to do is that we can take the floor function of both sides, right? So we round it down to the greatest integer, and so then we're going to have the floor, the log of x is equal to, now this part, remember, this part is less than 1. And so if it's less than 1, then when we take the floor of it, it's just going to go to 0. So then all we get is the digit count of x minus 1, and then we can solve for it as the digit count of x is equal to log base 10 of x plus 1. Now you might also want to rewrite this as the ceiling function. However, for example, if we count the digit count of 1, we want that to be 1, right? It's just 1 digit. Then it kind of breaks if we use the ceiling function instead. So we're just going to keep it with floor plus 1. And then there's also the added thing, which is that we want the digit count of 0 to be equal to 1. So this is just kind of an addendum to the formula, because you can't directly plug that in, since at 0 basically log x has an asymptote. But we're gonna take this, and you're gonna see that it still works well with concatenation and deconcatenation and other stuff like that. Now here's a couple other useful operations we could have based on the digits of numbers. We could define things like the digit sum and the digit reversal, like switching the digits around. Now, if we think about this, let's say, for example, the digit sum, we can literally think of it as simply the sum of the digits, like the kth digit, say, from 1 to the total digit count, right? And then if we want to do reversal, if we think about how each digit works in base 10 and what power of 10 it's multiplied by, we basically switch those around, but it's still a sum of 10 to the something, and then times basically kth digit from 1 to the total digit count. So again, this kth digit thing is appearing a lot, and so we want to properly define that first. So basically, if we want to have the nth digit of a number x, which I'm just going to, as you may have seen before, I denoted it as with the square brackets here and then subscript n, right? And so let's first think about the first n digits of the number. So if we have that, if we have the first n digits, then we can isolate the number on its own if we then subtract the first n minus 1 digits. Now we can't obviously do this subtraction directly. We want to just get that single digit left over at the end, right? So what we'll have to do is we have to take these first n minus 1 digits and then multiply it by 10. So now we can subtract that off, and then all we get left is that nth digit, right? So we can think about this like so. So basically, for the first n digits, we're going to have the number, and then we're going to divide by 10 to the digit count minus n, right? That's going to give us the first n digits, and there might be some decimals left over, so we're just going to take the floor of this to round it down. And now, so here we have basically the first n digits, and now we want to subtract off 10 times the first n minus 1 digits. So that'll just be 10 times, we have the same thing here, x over, and now it's going to be 10 to the digit count of x minus n minus 1, which basically turns into digit count of x minus n plus 1. So that's what we have, digit count of x minus n plus 1. And so now we have the nth digit well and defined. And so then with this, if we want to get the digit sum, then this is simply going to be, I'm going to denote it in a similar way. We have the square brackets here, but I'm going to do a little sigma for a sum symbol. And this is going to be, again, directly, simply the sum of its digits, right? So we take the sum, k is equal from 1 to the total digit count of each of the kth digits, right? So we can simply do it like that. And then if we want to also have the digit reversal, right? If we want to reverse each of the digits, which I'm going to denote with this arrow thing around the x like this. Now basically all we have to do is swap around the powers of 10 that each of the digits are multiplied by. So remember, the first digit is technically, like the first couple digits, those are the larger ones, and then they get smaller as you go towards the right. So then what we can basically just do is start with the first digit, go to the last digit, but instead of multiplying with the highest power of 10, we're going to start with the lowest power. So we start from 1, then 10, then 100, and so on. So this is basically going to be the sum, k is equal from 1 to the digit count of x of 10 to the k minus 1 times the digit count, or sorry, times the kth digit of x, right? So you start with the first digit, that's normally supposed to be the highest, but then you have the lowest power of 10, and it goes onwards like that. Now, with digit reversal also, notice that basically we know that the double reversal here should technically be always equal to x. It's kind of like it's kind of like an inverse if you do it twice, right? Like conjugation with complex numbers and that sort of thing. But it is not an exact inverse like this. All right, if you think about it, first thing that works, well, obviously x is equal to 0 works, right? Basically, it's easy to tell this works for any one-digit number. And but then the problem is if you have trailing zeros, when you reverse them, the 0 is going to go to the front, and basically it kind of disappears like that. So then if you're going to do the reversal one more time, then you lose on that 0. So it's sensitive to trailing zeros. So basically x is equal to 0, or any positive integer x, right, such that the last digit is not 0, right? So it's sensitive to zeros. And this is also a way that we can basically define palindromes this way, right? So this gives us a nice way to define palindromes, and we could potentially work with them in equations. Alright, now let's get to using some of these operations in equations. Mainly we're going to focus on concatenation and deconcatenation because those are easier to use in equations. So let's start off with a simple one first. Let's say we have 16 times x concat 2 is equal to 352. Now what we can do first, we can divide 16 on both sides. So then we're going to get x concat 2 is equal to 352 divided by 16, which is 22. Now notice we have a 2 here at the end, and then we also have concat 2. So what we can basically do is deconcat both sides. So we're going to get x concat 2 deconcat 2 is equal to 22 deconcat 2. And right here, these are going to cancel. This last 2 gets clipped off. And then we get that x is simply equal to 2. Now, we also want to check our answer to make sure that this makes sense. So if we check, we're going to have that 16 times 2 concat 2, which is going to be equal to 16 times 22, which we know is of course equal to 352. So this works. Now notice that we could have also done it using the more formulaic definition of concatenation, right? You could have rewritten x concat 2 as 10x concat 2. So then instead you would be solving 10x plus 2. You'd have 16 times 10x plus 2 is equal to 352. And then you just have a linear equation to solve, basically. Now, let's move on to a more complicated scenario. We're going to have x concat 3x concat 5 is equal to 125x plus 10. Now, if you want to think about the order of this here, basically you have to start with these two first and then you add it on like that, right? But anyways, I'm not going to show those brackets since it's kind of self-explanatory based on what we saw before. But so we have this extra 5 here. We want to turn it into simply just 2 parts of for concatenation, right? So let's say we deconcat 5 on both sides. So then we're going to have x concat 3x, and then remember that cancels with the concat 5, and then we're going to have 125x plus 10 deconcat 5, and then we can use the formula definitions of concatenation and deconcatenation to rewrite these. And now you might see here the problem is that we're concatenating with a second number that we don't know the digit count right away, right? So what we're actually going to have to do is at the end we're going to have to check for cases depending on the digit count of this one, of the 3x, right? And so this is going to make it take longer, and there could be, depending on the equation, quite a number of solutions. So it would be good to also just be able to prove past a certain point there are no more like integer proper solutions, and we're going to see that at the end. But so anyways, we're just going to use the definition now. So x concat 3x, that's just 10 to the digit count of 3x times x plus 3x. And now here for deconcat on the other side, we know what the second number is. That's just 1 digit. So we're going to have 125x plus 10 minus 5. And this is all divided by 10 to the 1, or just 10, right? And now you can multiply by 10, bring all the x's on one side, and factor some stuff out, and you're going to get 10 to the digit count of 3x plus 1 minus 95 times x is equal to 5. So now we can just solve for x by dividing this out. So we're going to have x is equal to, so 5, I'm just going to write the denominator first, over digit count 3x plus 1 minus 95. So this is what we have. And now we have to check some cases. So the first one we can see is if we check 3x is equal to 1, so 1 digit. in this case we're going to have x is equal to 5 over 100 minus 95, and this is simply 5 over 5, or 1. So this is what seems to be our first solution. But also, if you check further ones, it'll look like they're all turning out to be fractions, and so in your head you might think that this is probably the only solution, and that is correct, but we also have to show it. So we're going to basically have to find a way to prove that there are no more like proper integer solutions after this. So we have a ratio here. So a basic way we could just go is, well, you're going to have fractional results if basically the denominator here is greater than 5, right? We're going to have fractional results if 10 to the digit count of 3x plus 1 minus 95 is greater than 5, right? That intuitively makes sense. But anyways, if we solve this inequality, add 95 on both sides, divide by 10, and then we can take the log also, and then what we'll just get is that the digit count of 3x is greater than 1. And remember, this has to be an integer, right? So basically we already know that any number past this point, or any digit count past this point, is going to give you fractional results. So that means that 1 is the only solution, though we would also want to check this. So we'll do that real quickly right here. So we're going to check. So if we have 1 concat with 3 times 1 concat with 5, and this should be equal to 125 times 1 plus 10, right? So first we're going to get 13 concat 5 is equal to 135, and then of course we're just going to get 135 is equal to 135, and so this is a correct solution. There was also the potential to solve these kinds of equations numerically. Basically, you just need to, if you want to use Newton's method, you need to remember that the derivative of the floor function is 0 at non-integers and undefined anywhere else. So basically you can still differentiate properly and then do your iterations to converge to a root. And it should also be more exact, basically, since what you are expecting are integer solutions. Though you have to be kind of careful with your initial points, since they can kind of go a little bit more crazy. Or you can visualize this, like on Desmos. I put these operations together basically in a list, and then you can just visualize solutions that way too. And there are some interesting patterns for certain operations. So I kind of defined these formulas and their relations with equations a while back, but when I came back to it more recently, I also expanded to some newer operations. So I'll just mention these here. I haven't worked with them as much, but so basically there's also this idea of what if we have basically a form of concat multiplication, where basically if you have 3, for example, concat multiplied by 3, again we're putting the times with the circle and then the direct arrow, this is just going to be 3, 3, 3, right? Or if we have 12 concat multiplied 3 times, this is going to be 12, 12, 12. 12, 12, 12, like this. And we can actually solve for a formula based on a recurrence relation that we can find from the definition of just normal concatenation, right? So we can basically think of the general term as being the concatenation of the last term with the number itself again, or the unit basically. So if we think of this as some number x over here, then it's always the same digit count. It's always going to be 10 to the power of the digit count of x times the previous term, right? And then plus x one more time. And we can say that the first term, we want this to be x itself, right? And so we can solve this by basically just back substituting everything in. And so we can just get, so 10 to the digit count of x times 10 to the digit count of x, and then basically so on until we get to where we're using a1 here. 10 to the digit count of x times x plus x, and then these also have their plus x's on the outside. And then basically with these multiples, since we only go until a1, we don't have an a0 here, this power is going to be not 10 to the n times the digit count of x, but 10 to the n minus 1 times the digit count of x. And then this also is multiplied by x. And then we have the remainders, or like basically we multiply the remaining 10 to the power of x's times these x's over here, right? And then with this, we're going to have always one less than what we already had for this power. So that's just going to be plus n minus 2 of these, n minus 2 of 10 to the digit count of x times x. And then we just have the original plus x on the outside here. And then with this, you can further factor out an x and then simplify, and you will get basically, so this is x concat multiplied n times, this is going to be x times 10 to the n times the digit count of x minus 1 divided by 10 to the digit count of x minus 1. Now we can think about where this basically comes from also if we consider patterns of what we're multiplying by, basically what this whole ratio is, right? So if we think about 3 concat multiplied 3 times, then this is going to be, we want this to be 3, 3, 3. Now if we divide out by 3, then what we're going to get is 1, 1, 1. So there's basically this pattern here. So this is for one digit number. If you just multiply this by however, like n times, you have one of these ones n times, and then you just multiply by the number and you get that. But then if we also want to consider something with 2 digits, for example, again the 12 concat multiplied 3 times, we want this to be 1, 2, 1, 2, 1, 2. And then also if you divide this by 12, what you're going to get is you're going to get this sort of pattern where you have 100s now repeated. So it's 100, 100, and then 1. And now if you want to represent these as ratios, you'll see that basically you have repetitions of 9s over each other. So that's basically where you get 10 to some power minus 1, right? And so they basically conform in a way that they sort of generate this pattern that you can multiply by to then get the concat multiplication. Now, on the other hand, just like how we kind of created deconcatenation for usage in equations, we can also create a form of what I'll call concat division, which is basically if you have, again, so 1, 2, 1, 2, 1, 2, and then we'll use this symbol, concat divide by 3, then it'll just be one unit of this repetition. That's what we want it to be. It'll just be 12, right? And so with this, you can also just like how we solve for the deconcatenation formula, you can use the fact that we want this to basically be a sort of inverse of concat multiplication. So we'll have A concat multiplied by B concat divided by B, right? This should just be equal to A, and then you can basically invert and solve for A, and then you'll get your formula, which in this case, it's that, I should write this in blue, in this case, it is x concat divided and times, this is going to be, you'll see that you just basically have to flip these 10 to the sum powers minus 1. And now you notice that we need the powers or like the digit count of the original, right? We'll need a digit count of the original, but now we know that the new one here, if this is already something that has been concat multiplied, if the x has already been concat multiplied, then it's going to basically be n times the original digit count. And so if we want to get the original, we just have to divide by n. So we'll have x times 10 to the digit count of x divided by n. And then what used to be the normal n times the digit count of x is just x, the digit count of x itself, right? So then we just divide by 10 to the digit count of x minus 1. So you basically have this pattern. It's a multiplied relation. If you want to do concat multiplication, you got to multiply n and the digit count of x. If you want to do concat division, you're going to have to divide the digit count of x by n. So there's that sort of pattern. And now I also mentioned this before, but I'm going to go a little bit deeper into it. There's also basically index concat sums, right? So we saw before in some of those, like for the definition of deconcatenation, like when it's actually defined, we saw that we could kind of represent like how you have a part that you can actually clip off by this sort of concat sum. And there are some formulas which I found, which is that, so we're going to have this sum with an arrow going through it to show it's like direct, right? And so if we have this sum, concat sum, k is equal from 1 to n of some constant c, now we know that this is simply c concat c basically, and this is going to be n times, which we know is just equal to c concat multiplied by n. So there's that formula coming back again. However, there's also a sort of general, I'm going to put this in quotes, but like general term, you know how there is the sort of unit summation where you just have your k in there, and then unit product where you also have your k in there. Well, there's also this form here. If we have the concat sum, k is equal from 1 to n of k, which this is basically going to be 1 concat 2 concat 3, basically all the way until concat n, right? And I'm not going to show the details of this, but basically the formula that you'll get is 10 to the n plus 1 minus 9n minus 10 divided by 81. And you can basically use the fact that we have, again, another recurrence relation, that we have an is equal to 10 times the last term, right? You're always going to add that another 0, right? And then you can basically add the other digit, right? So then you'll add plus n, and then of course we know that we want a1 to be equal to 1, and then you can basically solve from that, and you'll get this. And now there's also the idea that, so we basically define this whole thing, which I would also like to call digit theory, because it's sort of like a subset of number theory. It has the potential to solve those kinds of problems, but it's based on operations of digits. And there's the potential that maybe we can extend this to any base of numbers, for example, base 2 with binary or hexadecimal or any other kind of base. So with this whole, if we extend to any base, we already have some formulas which if we try these for other bases, they already work by basically replacing the 10 with that base. So if we have, for example, the digit count of x in, I'm going to say in base b, I'll just do the subscript b, but basically this is now just going to be floor log base b of x plus 1 instead of log base 10, right? And what happens to also work is that if we have x concat y in base b, we can also just replace the 10 with a b. So we'll have b to the digit count of y times x plus y. So there's this potential that we can also extend this to other bases. Though for now, I'm normally keeping it in base 10 with the usual numbers that we work with. So I hope that you found this interesting, this kind of spiral we went through to invent this idea of operations on digits, to make concatenation more numerical and use them in equations and that sort of thing. So I hope you enjoyed this video and keep on staying curious, and I'll see you in the next one.